Welcome to this lecture in the 0006 series. Today we're going to talk about drying, which I accept is not a very interesting subject, but I'm going to do my best to make it as interesting as I can. So, if you haven't got one already, go get yourself a cup of tea or coffee, come back and let's make a start. So let's start by looking at what you should know by the end of the lecture. The first thing is, why do we dry solids in the first place? Why can a pharmaceutical material not just be wet and it be fine? So you should be able to discuss the reasons for drying materials in the first place. In terms of the drying process, we're going to look at something called the convective stages of drying, and that has 4 stages. So you should be able to describe the 4 stages of convective drying. We're going to look at that in the first half of the lecture, and then when we come back and we do the second part of the lecture, we're going to look at a number of drying methods. Those would be tray drying, fluidized bed drying, spray drying and freeze drying. So for each of those methods you should be able to explain how they work, and more importantly you should be able to say what type of sample you would dry with those particular methods. Now, a lot of people say to me, that's a very interesting subject, sir, drying. I don't know how you've made it so interesting, but what do I actually have to remember for the exam? Or another way of looking at that is to say, what type of exam questions are set? Right. So typically there are only a number of types of questions that I set for this type of topic, and they would be discuss the stages of convective drying and how it happens. It might be to focus on a particular type of drying. So let's say freeze drying is a good one. Freeze drying is based on the phase diagram of water. Now you might not know what that is yet, but you will do by the end of the lecture. So maybe a discussion about freeze drying. And then another type of question which really does test your knowledge of whether you've understood what I'm talking about is sometimes I give you a list of materials, pharmaceutical materials, and I ask you, which method of drying would you choose to dry this particular sample? So as we go through the lecture, when we talk about each drying method, I'm going to put up a table after we finish talking about each method, and it's going to summarise what type of material can be dried and the quantity of that material that can be dried. Okay, so type and quantity. Type is either a solid or a liquid. It can be a solution or a suspension. And quantity, it's typically either a small mass or a large mass. Okay, so what that means is you've got 4 combinations: solid, large mass; solid, small mass; liquid, large volume; and liquid, small volume. 4 types and 4 drying methods. And so what you will see as we go through is one type of drying method is appropriate for one of those samples. So if I set an exam question, it says, here are some examples of pharmaceutical materials. Which method would you choose to dry each material and why? It should be relatively easy. Just think about that table that I'm going to show you later to work out which is the most appropriate method. Look first at whether the material is a solid or a liquid, and then look at the volume or mass of the material. And that should tell you which drying method to use. Okay? You will thank me for that later in the year if there's a horrendous drying question on the exam paper. So, first things first, what do we mean when we say drying? Drying means the removal of water from an otherwise wet material. If you didn't know that, then I have to question why you're on this course in the first place. I think most people would understand what we mean by the word drying. For a pharmaceutical material, what sort of thing do we start with? We can start with a number of things actually. We can start with a wet solid. So your material, let's say it is a powder that's going to be compacted into a tablet. It might be wet granulated. So in order to mix the excipients together, you've added a bit of water to get some good mixing. So the material is otherwise a solid, but it has a water content that you don't want to be there. So wet solid. And the other two are solutions and suspensions. I'm pretty certain that you know what the difference is between those two, but for a solution, the drug molecules are dissolved, and for a suspension, the drug molecules are dispersed as particles actually. So why do we worry about, in particular, solids? Why would we worry about drying a solid material? Surely a lot of solids are already dry. So if I pick a good example, a table, let's say a table made of wood. I'm currently resting on a table made of wood, and you can't see it, but you can hear it. Okay, this table is pretty solid. I just hit it with my knuckles, and it feels dry. It looks dry, but actually it's not dry. It's going to contain an appreciable amount of water, probably about 10 to 20% of water. It's just that water is tightly bound in the cells of the wood, and so you can't actually feel it. You can only feel water that's at the surface of a material. It's kind of important that we recognise that for a material to have certain properties that we want, sometimes that material does actually need to contain water. If I were to dry the table that I'm sitting at completely to bone dryness, absolutely no water whatsoever, I would have a powder, a sawdust powder on the floor, because the water is really important in keeping the physical integrity of the wood. The same is true for you. Actually, I think you might imagine that most human beings are around 65 to 70% water. And if we removed all of the water from you, then you would also be a pile of biochemical compounds on the floor. You wouldn't actually be a recognisable human being. So when we say we're going to dry something, we're not necessarily drying it to complete dryness. We are drying it to a particular point that allows us to use that material to formulate. It's a little bit different for solutions and suspensions. No one would argue that you're going to take a solution and you're going to dry it a bit, because all that will do is remove some of the water and you just have a more concentrated solution. So we're not going to dry solutions and suspensions a bit. If we're going to dry a solution or a suspension, it's going to be to produce dry powder at the end. But even then, the dry powder itself may not be 0% water content, but we are effectively removing all of the water from a solution or a suspension. Okay? Why? Why do we want to do this? There are a number of reasons listed on the screen in front of you, but one is the physical form. So quite often when you're making something in a factory, working in a factory is completely different from working in a laboratory. In a laboratory you might wet granulate something, a very small amount of a powder, 20 grams or something like that, and you might dry it out and compress it into a tablet yourself. But in a factory you might be wet granulating half a ton of material, and that material has then got to be flowed around the factory to the next stage in production, so presumably a tablet press or something like that. I think you can imagine that a dry powder is going to flow a lot better than a wet powder. So if a powder has come out of a wet granulator, for instance, and it's a little bit wet, it will just be sticky and it won't flow very nicely around a factory. So one of the main reasons for drying powders in particular is to get them to process better. But there are some other ones. So if you think about chemical degradation in particular, a really common mechanism by which a lot of drugs degrade is hydrolysis. So hydrolysis means chemical reaction with water. So you're adding water across a chemical bond in the molecule. I think it stands to reason, therefore, that if a compound is susceptible to hydrolysis and it is formulated in a powder which is wet, the risk of hydrolysis is going to increase. So where a drug hydrolyzes, you might want to reduce the water content. Polymorphic forms. Don't tell me that you don't know what polymorphic forms is, because we talked about this a few weeks ago. Okay, so if you have a polymorphic form and it's metastable, and you allow that to get wet, water acts as a plasticizer. That means the water molecules get in between your drug molecules and they help to fluidize them. And moving from one polymorphic form to another just involves movement of molecules. So if the water gets into the sample and it helps the molecules to move about a bit, it generally helps them to crystallize to a different form. So if you are using a metastable, and in particular an amorphous form, keeping the water away from your material is really important, because otherwise it tends to crystallize to a stable form. There are a few others on here that you might not have thought about. So growth of microorganisms, maybe not so important in sort of wet solids, but certainly in solutions and suspensions. The risk of bacterial contamination is really high, and obviously bacteria like to grow in water. So if you've got something in there, maybe some oils or fats or some sort of carbon source, the bacteria have everything they need to grow. They've got a food source and they've got water. So if there's a risk of spoilage, then keeping something dry is usually safer. Corrosion. Corrosion's a good one. What can water do that can corrode something? So surely it's pretty harmless. The doctor tells you to drink water every day. Your mum probably tells you to drink more water. So it can't be that bad. It can be that bad. I don't know about you, but I've been to the Grand Canyon in America. It's nearly a mile deep in places, and that was carved by the Colorado River, which is just water. It's just water flowing through the scenery. And over hundreds of thousands of years, it has created a cavern that is a mile deep. Water can be quite aggressive. Have you seen a car from the 1970s? I realise that I'm a child of the 1970s and that you're not, but if you go outside, see many cars in the 1970s? No. Why not? It's because they've all rusted. Why have they rusted? It's an interaction between water and steel, and so it causes the formation of iron oxide, doesn't it? So water is a very corrosive material. It just depends on the context. So please don't stop drinking water. It's not corrosive inside you, but it can be very bad for materials, especially not just the material itself, but how it's stored or how it's processed. So imagine you're processing a material in a factory in stainless steel equipment. You really don't want a lot of water around there because ultimately it's going to start to corrode. Less with stainless steel, but nonetheless it's still difficult. The last two words on here are words that most people haven't heard of, and so were we doing this lecture for real, face to face, I'd ask you, what do you think efflorescence and deliquescence are? And then there'd be a period of silence while you thought about it. So we can at least recreate the period of silence while you think about what is efflorescence and deliquescence. Right, go, have a think. See, what I'm doing there is I'm rehydrating myself. It's very important. Efflorescence is a tricky one. If you have ever had a chocolate bar and you've left it in, say, a hot car, maybe it's gone through some temperature cycles. Maybe it's a really old chocolate bar and you found it at the back of the cupboard and you're really hungry and you open it. Have you ever seen a chocolate bar that's got sort of white powder on the top of it? So that white powder is actually fat that was originally dispersed in the chocolate bar, and because of the temperature cycling, that fat has been able to move through the chocolate, and when it reaches the surface, it crystallises at the surface of the material. So that process is called efflorescence. Didn't know that, did you? So you can say to someone, if they give you a really old chocolate bar and it's looking a bit powdery, you can say, no thank you, it looks like your chocolate bar has effloresced. And that's not an easy word to get into a conversation. So efflorescence is one, and because that involves movement of molecules, I think you might imagine that if the material gets wet, that encourages molecules to move, and so efflorescence can occur faster if the material gets wetter. The other one is deliquescence. So, I don't know if you know what that is, you might have heard of that actually. So when I was at school, we had watch glasses, and we used to put salts in particular in a watch glass. And so deliquescence means that a material has the propensity to absorb a lot of water from its surroundings. So you put a salt into a watch glass and leave it overnight, it absorbs so much water it actually dissolves itself and forms a solution. That's how strongly some salts can absorb water from their surroundings. So that process is called deliquescence. It's effectively a material dissolving itself. Okay? So we don't want any of those processes to occur in our pharmaceutical materials, and so that's the main reason why we dry them. How do we define moisture content? We're not going to say don't formulate that material, please, because it's a bit wet. A bit wet is not a helpful term. We don't know what a bit is, do we? So we have to have a way of defining a moisture content. In the blue box on the screen is the definition of water content. It's expressed as the mass of water in kilos per mass of dry solid, also in kilos. Right? Not too difficult. So a water content of 0.4, for instance, means you've got 0.4 kilos of water per kilo of dry solid. It's just an easy way of trying to describe how much water is present. Underneath that it says water is not just water. There's different types of water, and this becomes really important when we think about how we're going to dry a material in a moment. The first one says easily removed free water. This is my cup of coffee. I'm kind of hoping that you followed my instructions earlier and you also have a cup of tea or coffee. Can you imagine if I were to spill this cup of coffee onto the wooden table that you can't see? There will be coffee on the top of my table. The table would therefore be wet because there's coffee floating around on the top of it, and we would perceive that to be wet as well. If we touch the table, we're really going to get coffee on our fingers, aren't we? So that's water on top of a material. That's the easiest type of water to remove. I could, if I wanted to, just use a towel or a tea cloth or something and wipe the water away. That's one option. But it's the easiest to remove, even by evaporation. It's the easiest water to remove. It's sitting on the top of your material to be dried. Okay. The technical term for that is it's water which is exerting its full vapor pressure. Now you might not be interested in chemistry like I am, so don't worry about that definition. I'm just getting it in there because it's the technical term. So it's water that's free to exert its full vapor pressure, and it will evaporate the same as any other water in a beaker or something, because really the water molecules are interacting with themselves. It doesn't really matter that it's sitting on top of another material. The next one down is harder to remove bound water. So if we have water sitting at the surface of our table, because we've spilled our drink for instance, and we wipe it with a tea cloth, or maybe we just allow the water to evaporate over time with a little bit of heat or something like that, the water which is interacting with itself will evaporate off or be absorbed off very easily. But imagine if we wipe this table with a towel, have we truly removed all of the water from the surface of the material? The answer is no. There's going to be a layer of water molecules left behind because those water molecules are interacting with the molecules in the table in this instance, or any other material that happens to be wet. And so that's called bound water. So imagine the further away, if this is the surface of my material that we're trying to dry, you imagine we've got water on the surface as a layer. At the top here, the water molecules are interacting with water molecules. That's fine. It doesn't matter what surface it's on, it's just water. But as we get nearer to the surface of our solid, the water molecules start interacting with the materials in the substrate below. So if that interaction is kind of strong and there's a positive interaction between the water and the substrate, the water molecules nearer the surface are harder to remove, and so that's called bound water because the molecules are interacting with the substrate. After that, there are some water interactions where we probably aren't going to get involved in removing that water by drying. The first one is hydrates. Again, from the lecture we did last time about crystalline materials, a hydrate is a crystalline material with water in the unit cell. So that means if you've got one water molecule per one drug molecule, a 1-to-1 ratio, the material is a monohydrate. But it's in the unit cell. The water is there, and there's quite a lot of it, but it's in the crystal structure. It's not randomly on the surface of the material. And we probably wouldn't dry a material to remove that type of water, because you would turn the material from a hydrate to an anhydrous form, and those are two completely different things, right? So when we're talking about drying, we're probably not talking about removal of crystal lattice water. And then the other one is intracellular water, and I've alluded to this already. The table, you, oh, that's me, isn't it? Me, you, we all contain water within our cells, and we certainly, well, bacteria, we're certainly not going to be removing that water because it's going to desiccate the material and we're going to become powders. There is one exception to that, which is bacteria actually. So imagine a probiotic formulation. You're in year 2, so when you get into year 3 and you do the 0012 module, we're going to have a lecture about probiotics because it's one of my favourite subjects. And a lot of probiotics on the market are freeze-dried. And so that is the one instance where actually we do remove intracellular water from the bacteria. I know what you're thinking. You're thinking, which drying method do I use to dry bacteria, sir? That's what you're thinking. If you're not thinking that, you should be thinking it. And the answer is freeze drying, and we'll see why a little bit later on. Right, one more important concept, and then we can actually have a quick look at the 4 stages of convective drying. And then we can stop for a break. Tremendous. Right, that is, we have to think about what is the mechanism by which we dry a material in the first place. And it's a little bit of a concept which you may not have thought about. I don't know about you, whether you wake up in the morning and you think to yourself, I wonder how a material does dry. I don't know, but I've never woken up and thought that, so I'm trusting that you haven't. And so the answer is that a material is wet. It means it contains an amount of water, but it's surrounded by something. Usually, for the sorts of materials we're talking about at least, the surrounding space is air. So the material is surrounded by air. Even if you have a pile of wet granulated powder on a tray, it's still surrounded by air, isn't it? And air can also contain an appreciable amount of water. Again, I normally say this in class, but I used to go to Malaysia quite a lot to go and recruit students for our MSc programs. And one of the characteristics of being in Malaysia is every time I got out of a taxi, because when I'm not talking to camera at least, I'm wearing glasses. Every time I got out of a taxi, my glasses would instantly steam up. I used to do this with my son when he was young, but it's the same principle. Okay? They used to steam up. And the reason is because there's so much water in the air in Malaysia, because the relative humidity is so high. As soon as a cold, dry surface is exposed to the air, instantly the water condenses onto the surface, which is what's just happened with my glasses. So I want you to remember that we've always got an equilibrium between the material we're trying to dry and its surroundings. And usually the material is surrounded by air. How much water that the air can hold is called the relative humidity. If we saturate the air with water, that means that the air cannot take any more water molecules. It's holding as many water molecules as it possibly can. It's said to be 100% relative humidity. If the air is completely dry, 0% relative humidity. I'm sure you can appreciate this, but if you're in a car on a hot day and you've got the air conditioning running, or you're in an aeroplane, imagine you've gone on a long haul aeroplane flight and the air is being air conditioned. Air conditioning has the effect of reducing the relative humidity in the air, and so the air is very dry. And the reason they walk up and down the aisles in an aeroplane giving you water is because your throat's getting dry, because the relative humidity of the air around you is drying you out. All of the drying methods we're going to talk about operate on this principle, which is that because your material is surrounded by air, there's always going to be an equilibrium established between how much water is in your material and how much of that water is in the surrounding air. So let me give you an example. We have a material which has been wet granulated and has quite a high water content, and then we take it out of the granulator and we leave it and we put it into a box, and maybe we pump in absolutely dry desiccated air, so there's no water in the air, and we put a lid onto the box. What will happen is some of the water will evaporate from your wet granulated powder into the airspace, and when we open the box a few minutes later and we measure the relative humidity of the air, it would have increased because it's possible to absorb some water from the solid. And over time, if we leave it, the two materials will come into an equilibrium. There'll be a water content in your solid and there'll be a relative humidity in the air surrounding that solid. And once the position of equilibrium has been reached, there'll be no more change in water content of either the air or your sample. For every molecule of water which evaporates from the surface of your wet solid, another one condenses from the air back onto that solid. So that it's a dynamic equilibrium, but the actual water contents will never change. That's what's represented in the box at the bottom of the screen. What this means is we can then use this principle to dry the material. Okay, think about this. If we constantly keep the relative humidity of the air surrounding the sample low, it will force that equilibrium to keep going. So if we put the sample into a box, put a lid on, and we recognise that some of the water will evaporate into the air and then it will stop because the system's come to equilibrium. If we're constantly changing the air, so imagine we're constantly flowing dry air into that box, it will never get a chance to reach equilibrium, because every molecule of water that goes up into the airspace to increase the relative humidity, that air is then being removed and replaced with dry air. So the process keeps going because the system's trying to get to equilibrium. And that is the basis of most drying methods. We're just trying to disrupt the position of equilibrium between the water content of the solid and the environment surrounding that solid. You'll see later when we talk about the different drying methods actually. Okay. As long as you're okay with that principle, you're basically understanding how materials are going to dry. So that's a good thing. There's one more important thing on this slide, and it's the equilibrium moisture content, or EMC, and it is the position of equilibrium that I just talked about. So if you've got a relative humidity in your airspace of around 65 to 70%, and you've got a water content in your sample of say 10 to 12%, and the two are happily at equilibrium, we say that the water content of the solid is at its equilibrium moisture content. It means it's at equilibrium with the surroundings, and it doesn't matter what you do, there's going to be there's no net change in water content between the solid and its surroundings. So it's said to be equilibrium moisture content. Imagine that you've got a drying method, and it's based on dry air, and so it has the potential to dry your material all the way down to maybe 1 or 2% water content. Imagine that your material is then going to be stored in a blister pack, and it's going to be able to exchange water with the surroundings, and most people's houses are around 60 to 70% relative humidity. There's no point drying the material really low in water content, because on storage it's going to reach a new position of equilibrium with its 65 to 70% RH surroundings. So the material just re-wet and go back up in water content. So it's kind of important to understand what is the equilibrium moisture content of your material under its storage conditions, because there's no point drying that material below that, because it will just re-wet on storage. Okay? I strongly advise you to remember that point. It's really important. Right, before we stop for a tea break, I just want to run through quickly the 4 stages of convective drying. So on the screen in front of you is a graph. It should look like this, and it's got some vertical lines, and it says 1, 2, 3, 4. Okay, those show you what the water content of a sample is as a function of the time it's taken to dry. Starting on the left hand side, as you're looking at it at time 0, the water content is the highest. You start to dry, and you can see the line reduces and it goes through a curve, and that the 4 stages are kind of important. In stage 1, that line is linear. Oh, sorry, it's this way, isn't it? That line is linear. Okay, and the reason it's linear is because in that stage the material is really wet and the water is on the surface of the material, and that water is evaporating as if it was a free liquid. Like I said earlier, the water is interacting with itself, and so the evaporation rate will be the fastest, it will be linear, and it will also be responsive to how much heat you're applying. If you apply more heat, the water will evaporate faster. So you're going to end up with a line that will get steeper the faster you apply heat to the sample. But nonetheless, the rate of water loss is linear because the water is evaporating from the surface of the solid. If you look at the second phase, so the region that says 2 above it, it kind of looks to a first approximation like it's a linear region, but it's not. The rate is actually reducing slightly. So in region 1 it's linear, in region 2 it's a curve, in region 3 it's a curve actually. So 2 and 3, they're both curves, and so they're called falling rate periods because the rate of water evaporation is reducing. So region 2 and 3 are both falling rate periods. Why? Why does the water evaporation rate start to drop off? The answer is because once you've removed most of the water from the surface, the free water at the surface of the material, you don't have a lot of surface area of material left to evaporate, and the water that is evaporating, it's evaporating from the surface still, but the water is then being replaced by movement of water from capillaries. So the lines on this graph are capillaries, very fine lines, and the water is moving to the surface and then evaporating. And in the second falling rate period, you're just getting evaporation from within the capillaries. So in both those regions, essentially the surface area from which the water is evaporating is reducing, and so that slows the rate of evaporation. And at the end, so region 4, that's gone back to a linear line, but now the line is horizontal, and the reason is because there is no water evaporation anymore. The material is at its equilibrium moisture content, and so there's no more water loss because the system's at equilibrium. Every one water molecule that evaporates, another one condenses. So you've got these 4 stages. The first one is linear, the 2 in the middle are falling rate periods, and the last one is also linear. The only other thing to say is on that graph there's a little line that says CMC. What is CMC? It's the critical moisture content, and it's the point at which the water loss moves from being linear to non-linear. Okay, so that's just a technical term, but I thought I'd mention it. Right, with that, we're done for part 1 of the lecture. Go and make yourself another cup of tea, and I'll see you in a minute to talk about drying methods.